And a lot of times it's difficult to find the partial sum. And if you just need to know if the series diverges or converges, you can use one of these two tests. So for the divergence test, this is the official theorem, but I broke it down so that it's a little bit more obvious here. If the sequence AN doesn't have a limit, then we would say that the series diverges. If the sequence does have a limit and approaches some value that is not equal to 0, then we can also say that the series diverges. But the converse isn't necessarily true, and we call this that it's inconclusive. If we find that the limit of the sequence approaches 0, then there isn't enough information to draw any conclusions from that because the converse isn't true. So for example, if we look at this sequence, 1 over n, we know that as n approaches infinity, the sequence approaches 0. So the limit is 0 for this sequence. However, we know from the previous lesson that when we found the series of 1 over n, which is called the harmonic series, the series diverges. So there are cases when the sequence might approach 0 for the limit, but the series diverges, and there might be cases where the sequence approaches 0, but it converges. So this doesn't give us enough information. But the theorem does tell us if any of these are true, if the limit of the sequence doesn't exist, or if the limit of the sequence approaches some other value other than 0. In both cases, this diverges. So let's look at the first example. We want to use the divergence test to see if this series converges or diverges. Now, this doesn't tell us what the value of the series is. This just tells us if it diverges. So we're going to look at the sequence, which is n over 3n minus 1. We're going to take the limit as n goes to infinity and see what happens. So when I take the limit as n goes to infinity, I'm going to use the trick where I divide everything by n. So that gives me n divided by n on the top gives me 1. 3n divided by n gives me 3. And then 1 divided by n gives me 1 over n. And so that way, when I take the limit now, I can see that this approaches 0, and I'm left with 1/3. Now, because this is a value other than 0, we know that the series of n over 3n minus 1 is going to diverge. So if we look back up here, if either one of these cases is true, if the sequence doesn't have a limit, or if the sequence has a limit other than 0, we know for sure by this theorem the series diverges. Okay, let's look at the next example. We're going to look at the series of 1 over n to the third. If I take the limit as n goes to infinity of 1 over n to the third, we know that gives us 0. And so I can say that that divergence test here is inconclusive. For this last example for using the divergence test, if I take the limit as n goes to infinity, this n squared gets larger and larger, which means this whole fraction gets smaller and smaller and approaches 0. And e to the 0 is 1. So because this is something other than 0, we can say by the divergence test that this sequence diverges. So this divergence test is basically just telling us if it diverges or not. It doesn't give us any information if it converges. It's just giving us information how to check to see if it diverges. The next test we're going to look at is called the integral test. Now, this test is called the integral test because it compares an infinite sum to an improper integral. So what this integral test is telling us, if we have a series and I can make this sequence, an, if I can view it as a function where the function is continuous between 1 and infinity, if the function is decreasing, and if the value of the function at n is an, then we can use this trick to make a comparison. If this integral diverges, then the series diverges. If the integral converges, then the series diverges. But it's only after making sure that these conditions hold true. So let's look at our first example using the integral test. When I look at this series, if I think of 1 over n to the third as a function, so now I'm thinking about it in terms of x's instead of n's. So if I think of it as 1 over x to the third, these are the conditions I want to check to see if they hold true in order to use the integral test. Is 1 over x to the third continuous from 1 to infinity? And that would be a yes. If we were looking at it over all the real numbers, we would say no, because it's discontinuous at x equals 0. But in this case, it's continuous from 1 to infinity, so this works. Is it a decreasing function? On the interval from 1 to infinity, it certainly is decreasing. As the denominator gets bigger, the whole fraction gets smaller and smaller. Is the value of the function the same as the sequence if I plug in values for n that are the same for x, where x and n overlap, right? So if I plug in, say, n is 2, is that the same? Am I going to get the same answer as plugging in x is 2 here? That's what this is saying. And that's true. So it meets all of these conditions, so I can use the integral test. So if I find the improper integral, what that value is from 1 to infinity of 1 over x to the third, if this integral diverges, then the series diverges. If this integral converges, then the series, we can say, converges. So when I set this up, the integral from 1 to infinity of 1 over x to the third dx, I'm going to rewrite that as a proper integral. And I have the limit as t goes to infinity of the integral from 1 to t, 1 over x to the third dx. Now, when I integrate 1 over x to the third, I get 1 over negative 2x squared. And I want to evaluate that from 1 to t. When I evaluate this from 1 to t, I get negative 1 over 2t squared plus 1/2. This becomes a plus because this is a negative, and then when we subtract that second term, when we evaluate it, it changes to a positive. And then as we take the limit as t goes to infinity, the denominator gets bigger and bigger, so the whole fraction gets smaller and smaller. So this fraction here approaches 0 as t approaches infinity. And so then we're left with 1/2. So this tells us by the integral test, we know that this series converges because the integral converges. Now looking at this second series for this example, this is definitely continuous over the interval from 1 to infinity. It's discontinuous at 1/2. That's what we're concerned about. But from 1 to infinity, this is continuous. So that checks the first box. The second box, is this a decreasing function if we look at this in terms of a function? And as the denominator gets bigger, the whole fraction gets smaller. So this is going to be a decreasing function. And then the last thing we need to check, if I start plugging in values of n, is that going to be the same thing as if I plug in x? Am I going to get the same thing? So if I plug in, say, n is 3, am I going to get the same thing as if I plug in x is 3 here? And that would be true. So it meets the 3 criteria, so we can use the integral test. So I'm going to set up an improper integral from 1 to infinity of 1 over the square root of 2x minus 1 dx. I'm going to rewrite it as the limit as t goes to infinity from 1 to t of 1 over the square root of 2x minus 1 dx. Using substitution to to evaluate this, I'm going to let u be 2x minus 1. So then 1/2 du is dx. So when I rewrite it, I get this. When I evaluate it, I'm going to find that I need to take the limit as t goes to infinity of the square root of 2x minus 1. And I'm going to evaluate that from 1 to t. When I do that, I get the limit as t approaches infinity of the square root of 2t minus 1, and then minus 1 on the outside of the square root. And as t gets bigger and bigger, this whole value gets bigger and bigger, so this diverges. Now, because the integral diverges, we can say that the series diverges using the integral test. Now, we have something that's called a p-series. And a p-series is when you have a series set up in this form, where you have the sum from 1 to infinity of 1 over n to some power. Now, we have found that when it's in this form, if p is less than or equal to 0, we know that this diverges. If p is greater than 1, we know that this converges. And we can always check it using the integral test. So to convince ourselves that this is true, we're going to show both ways using the p-series and the integral test. We're going to show that this series converges. Now, this is set up in the form of a p-series because I have 1 over n to some power. My p is 4 in this case, which is greater than 1. So when we think of it in terms of the p-series, we know that it converges because the p is greater than 1. But if we double check it using the integral test, what we just learned, you can set up an integral from 1 to infinity of 1 over x to the 4th dx. And then you can check to make sure that all those 3 criteria are met. So I can tell you that they are met, but you can check them individually if you want. And then if we set this up as a limit as t goes to infinity from 1 to t of x to the negative 4 dx, when we evaluate, we end up getting the limit as t approaches infinity of x to the negative 3rd over negative 3 from 1 to t. When we evaluate that, we end up getting 1/3. And by the integral test, because the integral converges, we know that the series converges. So we check that it converges 2 ways, using the fact that we know what the values of p are in the p-series that converges, and then we also checked it using the integral test. Looking at this p-series, we have that our p is 2/3, which is less than 1. I would say that this diverges. Checking it using the integral test to convince ourselves that this is true, we set up our integral 1 to infinity of 1 over x to the 2/3 dx. We check to make sure the 3 criteria are met for the integral test, and they are. So then I go through the process of evaluating that improper integral, and we get, after we evaluate all of it, we get that this integral diverges. And so by the integral test, we can say that the series diverges. So we knew that it diverged because p was less than 1, and this is a p-series, but we also checked it using the integral test. In this last part of the lesson, we're going to talk about how we can estimate the value of a series. Now, the first thing we need to make sure is that we know that the series converges. And if we meet these following conditions, then we can use this trick, okay? So we need to make sure that if we imagine that sequence is a function that is continuous from 1 to infinity on that interval. We also have to make sure that if we imagine the sequence as a continuous function, that it is decreasing on the interval from 1 to infinity. And then the last condition that needs to be met is that if we plug in values of n like we would for the sequence, it has to come out the same if we imagine it as a function or if we imagine it as a sequence. Those values have to be the same. Now, n is determined by how accurate we want to be. So if I want to say find the fifth partial sum, and then I find the 100th partial sum, which means, a quick review, if I want to find the fifth partial sum, that means I find the first 5 terms of the sequence and I add them up. The 100th partial sum would be if I add up the sequence up to term 100. If all those added up together would be the 100th partial sum. So if I want to be more accurate, I'm going to use the 100th partial sum because that's going to be adding up more of the terms. The more terms we add up, the more accurate our estimation is going to be. But the question is, how far out do we go for n to meet within a certain error? If we think back to the previous lesson, one of the series that we looked at that we found that was convergent was the series from 1 to infinity of 1/2 raised to the power of n minus 2. And we found that that series was equivalent to 4. Now, if I find, let me go out, see, summation. Okay, I'm going to do that series. Let's say I go out to 20 instead of infinity, and I take that series of 1/2 that's raised to the power of n minus 2. I'm going to use x's here because that's the variable I have on my calculator. If I find the series and I only go out to 20 for my partial sums, then I'm going to get 3.9999. So it's pretty close to 4, which we found that the series was 4 when we went from 1 to infinity. Now, if I did that same thing, but I only went out to 10, let me make this adjustment. If I only added up the first 10 terms, it's not going to be as accurate. We know that the answer is 4 because we found it in our previous lesson. Notice that this partial sum, because I went out to 20, is a lot more accurate than if I only go out to 10. Now, if I want to find out what the error is, it would be whatever's left over. So if I know the exact value is 4, but let's say I only use the partial sum of 10 as an estimate, if I take 4 minus that value that we estimated, so this 4 is the series, the exact value for the series from n is 1 to infinity. This 3.996 is the partial sum out to 10. So we're not going all the way out to infinity. But if I find that difference, that will give me the error, okay? And then we see here that the farther we go out for our partial sum, the more accurate it's going to be. And that difference will give us the error. So this remainder estimate from the integral test, this theorem tells us we can estimate the error even if we don't know what the exact value of the series is by using the integral from whatever n we pick. If we were choosing n is 10 and we only go out to a partial sum of 10, then we would put 10 here. We go from 10 to infinity, and we would know that that remainder is going to be less than this integral. So this is a way we can estimate the error if we don't know the exact value to subtract. So now looking at this, it says we're going to calculate the partial sum of 10 for this series of 1 over n to the third, and we're going to estimate the error. So if we want to find the partial sum of 10, that means I'm going to take all the terms of 1 over n to the third out to the 10th term and add them up. That's my partial sum for 10. And when you do that on your graphing calculator, you get 1.19753. So we can use this 1.19753 to estimate this series. Now to see how far off we are, to see what that error is, we can use this theorem that we just talked about right here. Since we went out for the 10th term, we can estimate our error as going from 10 to infinity of the function 1 over x to the third. So to estimate the error, we go from 10 to positive infinity of 1 over x to the third. Because this is an improper integral, I got to change it to the limit as t goes to infinity. And I go through that process of evaluating that integral, and I end up getting the limit as t goes to infinity of negative 1 over 2x squared, evaluated from 10 to t, gives me this. So when I plug in t, I get minus 1 over 2t squared. And when I subtract what I get when I plug in 10, that gives me a positive because I get a double negative. And then I get 1 over 200. And now when I take the limit as t goes to infinity, this first term is going to approach 0 because the denominator is going to get bigger and bigger and bigger, so the whole fraction is going to get smaller, which then leaves me with just 1 over 200. So we can estimate that the sum, the partial sum going out to 10, gives us 1.19753, and that's going to give us an error of less than 0.005, which is the 1 over 200. So we got pretty close using S10. Now, if I went out to S11, it would be more accurate, so this error should be smaller, and we would just go through the same process, but instead of using 10, we would use 11 here. And this is a way you can estimate your error. Now, if you knew exactly what the value of the sequence is to find the error, you just find the exact value of the series and subtract your partial sum. But most of the time, that's not going to be the case, and that's what this theorem is telling us. We can estimate the error by integrating from n to infinity. But remember, it has to meet these three conditions for that to be true. Now, we can use this theorem to even work backwards, figure out what value of n, what term do I need to go out to for the series, and to add all those up, what term do I need to go out to in order to have a certain error? So we can use this to go backwards. So if I want to find the smallest value of n necessary so that our partial sum will give me an estimate for this series within 0.001, we figured it was, when we did it with 10 up here in part A, we got an error of 0.005. We want it to be less than 0.01. So we've got to go further out than 10 if we wanted to have an error of 0.001. So what we would do, we would just integrate from n to infinity generically. So instead of evaluating it specifically at 10, I would put in capital N here, and we would generically get 1 over 2n squared. That's what this is here. But when we plugged in 10, we got 10 squared is 100, 100 times 2 is 200. So that's where this is coming from because we plugged in 10. But if I just use the generic letter n and put it in here, we would have gotten 1 over 2n squared. And since I want this 1 over 2n squared to be less than 0.001, I just set up that inequality and solve. So when I solve this inequality, 1 over 2n squared is less than 0.001, I get that n has got to be greater than 22.36. And because when we're dealing with series, we're talking about discrete values, right? So they're going to be the whole numbers. So we're going to go to the next whole number up, which is 23. So we're going to say we have to go out to the 23rd term so that our error is within 0.001 of the actual value of the series. So when you want to work backwards to figure out what your value of n is, what number term you have to go out to, you just use capital N here instead of a specific value and set up an inequality here to solve for that value of n. And then you know that how far you have to go out to be within a certain error. Okay, so quick summary of what we talked about. We talked about the divergence test. which tells us if a series diverges, but it doesn't necessarily tell us that it converges. It just tells us for sure if it diverges under certain conditions. We talked about the integral test, where we compare series to improper integrals to decide whether or not the series converges or diverges, and it's got to meet some conditions in order to be able to do that. We talked about p-series, and when p is less than 1 or equal to 1, it's going to diverge. If it's greater than 1, then it's going to converge. And then we talked about using partial sums to estimate the value of a series, and we know that the further we go out in our terms and we add them up for our partial sums, the more accurate the estimation is going to be for the series.